Welcome! In this session, we will explore LeetCode problem number 863, titled All Nodes Distance K in Binary Tree. This problem is an excellent opportunity to enhance your understanding of tree traversal techniques, graph representation of trees, and breadth-first search, BFS. Let's dive in and break it down step by step. In this problem, our goal is to find all nodes in a binary tree that are exactly a given distance, k, away from a specified target node. The tree is represented by its root, and the target is guaranteed to be a node within the tree. The result should be an array containing the values of these nodes, and the order of the values in the array does not matter. For the input format, we are given the root of a binary tree, the target node, which is of type tree node, and an integer k that falls in the range from 0 to 500. For the output format, we need to return a list of integers representing the values of the nodes that meet this distance condition. Let's consider an example to understand the problem better. Suppose the binary tree is structured as shown, with the root node having a value of 3. Its left child is 5, and its right child is 1. Further, node 5 has children 6 and 2, while node 1 has children 0 and 8. Node 2 itself has children 7 and 4. Here, the target node is 5, and we are looking for nodes that are exactly 2 units away from this target. At distance 2, we find nodes 7 and 4 in the subtree of node 5, and node 1 in the other branch of the tree. Thus, the output is an array containing the values 7, 4, and 1. Remember, the order of the values in the array does not matter. Now, let's look at another example where the tree has only one node, which is 1. Here, the target node is also 1, and we are tasked with finding nodes that are at a distance of 3. Since the tree contains only this single node, there are no other nodes available at any positive distance. Therefore, the output for this case is an empty array. Finally, in a third example, we have a binary tree structured with a root node 0, which has a left child 1. Node 1 further has 2 children, 3 and 2. Here, the target node is 3, and the distance k is 1. The only node at a distance of 1 from the target is node 1, which is the parent of node 3. Hence, the output is an array containing just the value 1. To summarize, the constraints ensure that the tree has between 1 and 500 nodes, all values are unique, and the target is guaranteed to be a valid node in the tree. Key edge cases to consider include trees with a single node, k being 0, the target being a leaf node, and cases where k exceeds the height of the tree, all of which can result in specific predictable outputs. To solve the problem of finding all nodes at a distance k from a given target node in a binary tree, there are several approaches we can consider, each with its own strengths and weaknesses. One straightforward method is the brute force approach. The intuition behind this strategy is to calculate the distance from the target node to every other node in the tree. Using a depth-first search, we can traverse the entire tree and, for each node, determine its distance to the target. Once we have the distances, we collect the nodes that are exactly k distance away. However, this approach is highly inefficient because it involves repeatedly traversing the tree for each node, resulting in a time complexity of n squared, where n is the number of nodes. This redundancy makes it impractical for larger trees. A more efficient solution is to convert the tree into a graph. Here, we treat the parent-child relationships as undirected edges and use breadth-first search to locate nodes at the desired distance. This graph-based method avoids redundant calculations and significantly improves efficiency, making it a better candidate for larger trees. To implement the graph-based approach, we start by constructing a graph representation of the binary tree. Using a depth-first search, we create an adjacency list where each node is a key, and its connected nodes are stored as values. Once the graph is built, we perform a breadth-first search starting from the target node. During the BFS, we maintain a visited set to ensure that no node is processed more than once. We continue the BFS level by level until we reach the nodes at exactly k distance, which we then collect. This approach is both time and space efficient, with a complexity of n, due to the graph construction and traversal. Another alternative to consider is the DFS with backtracking method. Instead of explicitly converting the tree into a graph, we simulate the traversal directly. Here, we first use a DFS to identify the path from the root to the target node. For each node along this path, we calculate distances to all descendants recursively. Then, using backtracking, we compute distances to nodes in the opposite direction, moving up the tree. While this approach avoids creating an adjacency list, it still achieves a linear time complexity O, n, and uses space proportional to the tree height, O, h. The graph-based approach stands out as the most robust and intuitive solution to this problem. Its efficiency, simplicity, and scalability make it the preferred choice. With a linear time complexity of O, n, this method ensures that both graph construction and BFS traversal are optimal. By representing the binary tree as an undirected graph with an adjacency list, we simplify the problem of finding nodes at a specific distance. This representation allows us to easily handle both upward and downward traversals, which would be more complex in a purely tree-based approach. Additionally, this method scales well to larger trees without the risk of recursion stack overflow, as seen in the backtracking method. The key insight here is recognizing that the problem can be reframed as finding nodes at a specific distance in an undirected graph. By modeling the tree this way, we take advantage of BFS, which is naturally suited to level-based traversal. The aha moment lies in realizing that adding parent-child edges to the graph seamlessly accounts for upward traversal, eliminating the need for additional logic. When comparing these approaches, there are several trade-offs to consider. Using graph conversion requires extra space for the adjacency list, but it simplifies the traversal logic and avoids the risk of deep recursion. On the other hand, the brute force approach, while conceptually simpler, is far less efficient due to redundant distance calculations, making it unsuitable for larger trees. The graph-based BFS method also outperforms backtracking in terms of implementation complexity. While backtracking eliminates the need for an explicit graph, it involves intricate recursive logic that can be more challenging to debug and maintain. Ultimately, the graph-based approach strikes the best balance between efficiency, simplicity, and scalability. It avoids the pitfalls of both brute force and backtracking, offering a solution that is not only optimal but also easier to reason about and implement. The problem, all nodes distance k in binary tree, asks us to identify all nodes that are exactly k edges away from a given target node in a binary tree. To solve this, we need to consider the tree's structure. In a binary tree, parent nodes are aware of their children, but children don't know about their parents. This one-way relationship limits our ability to traverse the tree in all directions. To address this, the first step in the algorithm involves converting the binary tree into a graph representation. Here, we treat each node as a vertex and create bidirectional edges between parents and their children. This allows us to move both upwards to parent nodes and downwards to child nodes. Using a depth-first search, we build an adjacency list. For every node U, we add U to the adjacency list of its left and right children, if they exist, and vice versa. This adjacency list will serve as the foundation for the next steps of the algorithm. Once we have the graph representation, the next step is to perform a breadth-first search, or BFS, starting from the target node. BFS is particularly suited for this problem because it explores all nodes at a given distance before moving to the next level, guaranteeing that nodes are visited in order of increasing distance. We begin by marking the target node as visited and adding it to a queue. The queue helps us process nodes level by level, starting with nodes at distance 1. For every node in the queue, we examine its neighbors and add unvisited ones to the queue, marking them as visited to avoid revisiting them. This process continues until we reach distance k. At that point, we collect the nodes currently in the queue into our result list. By stopping the search once we reach distance k, we avoid unnecessary computation beyond what the problem requires. Finally, we return the result list containing all nodes at the desired distance. There are three critical insights that make this algorithm effective. First, representing the binary tree as a graph is essential. This transformation allows us to traverse both upwards to parent nodes and downwards to child nodes, overcoming the inherent one-directional structure of a binary tree. Second, the use of BFS is optimal for this problem. By processing nodes level by level, BFS ensures we only explore nodes at the required distances, avoiding unnecessary work. Finally, managing visited nodes is crucial. By maintaining a visited set, we prevent cycles and redundant exploration of nodes. This ensures that each node is processed exactly once, improving both the correctness and efficiency of the algorithm. The algorithm relies on three key data structures to function effectively. First, the adjacency list is used to represent the binary tree as a graph. Each node points to a list of its neighbors, including both its parent and children. This structure is efficient for accessing directly connected nodes during BFS. Second, the queue enables the BFS traversal. By following a first-in first-out order, the queue ensures that nodes are processed level by level, which is essential for finding nodes at an exact distance. Finally, the visited set tracks nodes that have already been processed. This prevents cycles and redundant exploration, ensuring that each node is visited only once. Using a set for this purpose is efficient because membership checks and insertions are performed in constant time. Let's analyze the algorithm's time and space complexity. Constructing the graph using the adjacency list requires O(n) time, where n is the number of nodes in the binary tree, as we process each node exactly once during the DFS. The BFS traversal also takes O(n) time, since each node is visited once during the search. This makes the overall time complexity O(n). In terms of space complexity, the adjacency list requires O(n) space to store the graph. The BFS queue and visited set also require O(n) space in the worst case, leading to an overall space complexity of O(n). Now, let's consider a few edge cases. If k equals 0, we simply return the target node itself. If k is greater than the height of the tree, no nodes exist at that distance, so the result is an empty list. In cases where the tree consists of only a single node, we must handle the scenario where the root is both the tree and the target node. Finally, we must ensure that the target node exists in the tree before beginning the BFS traversal to avoid unnecessary computation. To solve the problem of finding all nodes at a distance k from a target node in a binary tree, we start by converting the tree structure into a graph representation using an adjacency list. This makes it easier to perform graph traversal algorithms like breadth-first search. First, we define a helper function called buildGraph that recursively traverses the binary tree. For each node, it adds edges between the current node and its parent, as well as between the current node and its children. If the current node is null, we simply return without doing anything. Inside this function, we handle the left and right children of the node by adding them to the graph and making further recursive calls. Once this recursive process is complete, we have the entire tree represented as an adjacency list stored in a dictionary called graph. Next, we initialize a BFS algorithm to find nodes at the desired distance. We use a queue to keep track of nodes along with their current distances from the target, and we also maintain a visited set to avoid revisiting nodes. At the start, the queue contains only the target node with a distance of 0, and the target is marked as visited. Finally, an empty list result is prepared to store nodes that meet the distance condition. The BFS process begins by iterating through the queue. For each node in the queue, we check its current distance. If the distance equals k, we add the node to the result list and skip further exploration for that node. Otherwise, we explore its neighbors by iterating through the adjacency list. For each neighbor, if it hasn't been visited yet, we mark it as visited and add it to the queue with an increment distance. This ensures that we systematically explore all nodes layer by layer, starting from the target node. The BFS continues until the queue is empty, meaning all reachable nodes have been processed. Finally, once the traversal is complete, we return the result list, which contains all nodes that are exactly k distance away from the target node. This approach is efficient and leverages the graph representation to simplify the problem of navigating the binary tree. Here, we start by defining the method distance k, which takes in the root of the binary tree, the target node, and the distance k. The first step is to convert the binary tree into a graph representation. This is done using a hash map where each node value maps to a list of its connected neighbors. The buildGraph method will handle this conversion by traversing the tree and linking each node with its parent and children. Once the graph is built, we use a breadth-first search, BFS, to find all nodes that are exactly k steps away from the target node. A queue is used to facilitate the BFS, where each entry contains a node and its current distance from the target. We also maintain a visited set to avoid revisiting nodes and prevent infinite loops. The algorithm begins by adding the target node to the queue with a distance of 0 and marking it as visited. As the BFS progresses, we dequeue nodes one by one. For each node, we check if its distance from the target matches k. If it does, we add it to the result list. Otherwise, we explore its neighbors by iterating through the graph. For each unvisited neighbor, we mark it as visited, increment the distance, and add it to the queue for further exploration. This ensures that we systematically explore nodes layer by layer. Once the queue is empty, meaning we've processed all reachable nodes, we return the result list containing all nodes that are exactly k distances away from the target. The build graph method, which we called earlier, is crucial to this process. It recursively traverses the binary tree, linking each node to its parent and children in the graph. If the parent node exists, it creates bidirectional edges between the parent and the current node, ensuring the graph correctly represents the tree structure. Finally, we define the tree node class, which represents the structure of a binary tree node. Each tree node has a value, a left child, and a right child. This class is essential for constructing the binary tree input that the distance k method operates on. With this definition, we can build the tree, pass it to our solution, and retrieve the nodes at the specified distance from the target. This completes the implementation, providing an efficient way to solve the problem by combining tree traversal, graph representation, and BFS. To solve this problem, we begin by constructing a graph representation of the binary tree. The tree is shown here, and our target node is 5, with k equal to 2. We will transform this tree into a graph using an adjacency list. Starting with the root node 3, we add edges between 3 and its children, 5 and 1. Next, we move to node 5 and add edges between 5 and its children, 6 and 2. Similarly, for node 1, we add an edge between 1 and its child, 8. Finally, for node 2, we add edges between 2 and its children, 7 and 4. This step ensures that every node is connected to its neighbors, creating an undirected graph representation of the tree. Once the graph is complete, it looks like this: 3, 5, 1, 5, 3, 6, 2, 1, 3, 8, 6, 5, 2, 5, 7, 4, 8, 1, 7, 2, 4, 2. With the graph ready, we perform a breadth-first search, BFS, starting from the target node 5. We initialize our queue with the target node in distance 0, dec. 5, 0. We also maintain a visited set to avoid revisiting nodes, starting with 5 and an empty result list. At distance 0, we process node 5 and add its neighbors 3, 6, and 2 to the queue. The queue becomes dec. 3, 1, 6, 1, 2, 1, and the visited set updates to 5, 3, 6, 2. At distance 1, we process nodes 3, 6, and 2. For node 3, we add its neighbor 1 to the queue. For nodes 6 and 2, we add neighbors 7 and 4. The queue now contains dec. 1, 2, 7, 2, 4, 2, and the visited set updates to 5, 3, 6, 2, 1, 7, 4. Finally, at distance 2, we process nodes 1, 7, and 4, collecting them into the result list. The output for this example is 1, 7, 4. In the second example, the target node is 7, which is a leaf node, and k is 3. The graph remains the same as in the previous example, so we proceed directly to BFS. We initialize the queue with the target node 7 and distance 0, dec. 7, 0. The visited set starts as 7, and the result list is empty. At distance 0, we process node 7 and add its neighbor, 2, to the queue. The queue becomes dec. 2, 1, and the visited set updates to 7, 2. At distance 1, we process node 2, adding its neighbors 5 and 4 to the queue. The queue becomes dec. 5, 2, 4, 2, and the visited set updates to 7, 2, 5, 4. At distance 2, we process nodes 5 and 4, adding their neighbors 3 and 6 to the queue. The queue becomes dec. 3, 3, 6, 3, and the visited set updates to 7, 2, 5, 4, 3, 6. Finally, at distance 3, we process nodes 3 and 6, collecting them into the result list. The output for this example is 3, 6. In this example, the target is the root node, 3, and k is 1. Since the graph remains unchanged, we can directly begin the BFS. We initialize the queue with the target node 3 in distance 0, dec. 3, 0. The visited set starts as 3, and the result list is empty. At distance 0, we process node 3, adding its neighbors 5 and 1 to the queue. the queue becomes dec 5, 1, 1, 1, and the visited set updates to 3, 5, 1. At distance 1, we process nodes 5 and 1, collecting them into the result list since their distance matches k. The result list becomes 5, 1. There are no further nodes to process, so the output for this example is 5, 1. This demonstrates how the BFS efficiently collects all nodes at distance k from the target, regardless of whether the target is in the middle, a leaf, or the root of the binary tree. In this problem, our solution has two main steps: building a graph representation of the binary tree and performing a breadth-first search, or BFS, to locate nodes at a distance of k. First, let's focus on building the graph. The buildGraph function ensures that every node in the binary tree is visited exactly once. For each node, we process its parent and, at most, two children left and right. Since a binary tree with n nodes has exactly n1 edges, this step completes in n time. Next, we have the BFS step. Here, we visit each node in the graph and explore its immediate neighbors. With n nodes in each edge being traversed only once, the BFS also operates in n time. When we combine these two operations, the overall time complexity of the solution is n. Now let's analyze the space complexity of this approach. First, we consider the graph representation. Using an adjacency list stored in a defaultIct, we allocate space for n keys corresponding to the nodes, and n1 edges for the parent-child relationships. This requires n space. Next, the visited set is used to track processed nodes during BFS. In the worst case, all n nodes will be visited, so this also requires n space. The BFS queue temporarily holds nodes to be processed, and in the worst case, this queue could contain all nodes, making its space usage n as well. Finally, the result list stores nodes at distance k. While rare, it's possible for all n nodes to satisfy this condition, resulting in n space usage. When we sum these, the overall space complexity for the solution is n. Combining the components of space usage, we conclude that the total space complexity is n. Now, let's consider the best, average, and worst-case scenarios for this problem. In the best case, the binary tree has only one node, the root, and k equals 0. Here, the graph building step processes just one node, and the BFS terminates immediately, leading to a time complexity of 1. In an average case, the tree is balanced, and k is relatively small compared to the tree's height. Even in this case, the complexity remains n, because we still traverse all nodes during graph construction and potentially during BFS. The worst case occurs when the tree is highly unbalanced, resembling a linear chain, and k equals the tree's height. Despite this extreme scenario, the time complexity remains n, as each node is visited only once in both the graph building and BFS steps. Finally, let's compare this graph-based solution to a naive approach that uses recursive depth-first search, or DFS, to locate nodes at distance k. The naive method would require traversing the tree multiple times, once for each node, resulting in a time complexity of n squared, in the worst case, such as when the tree is a linear chain. By contrast, our graph-based solution is far more efficient. It converts the tree into a graph in n time, and the BFS finds all nodes at distance k in a single traversal. This optimization reduces the overall time complexity to n. To mathematically validate this, note that building the graph and performing the BFS each take n, leading to a total time complexity of n plus n equals n. Similarly, the space complexity stems from the graph, visited set, queue, and result list, each of which requires n space. Together, this confirms the combined space complexity is n. One common mistake when solving this problem is ignoring the bidirectional nature of the tree's relationships. While it's natural to think of binary trees as flowing from parent to child, this problem requires you to consider both child-to-parent and parent-to-child traversal. This is because finding nodes at a distance k from the target may require moving upward in the tree, not just downward. Another frequent oversight is neglecting edge cases. For instance, when k equals 0, the output should simply be the target node, and when the tree is null, the result must be an empty list. Missing these edge cases can lead to incorrect results or even runtime errors. Lastly, inefficiency is often an issue. Relying on multiple separate traversals, like one to locate the target node and another to calculate the nodes at distance k, leads to redundant computations. Instead, combining these steps into a single traversal can significantly improve performance and reduce complexity. Another critical mistake is improper graph conversion. When transforming the tree into a graph for bidirectional traversal, missing nodes or edges can result in incomplete or incorrect paths, making it impossible to reach all the nodes at the desired distance. It's essential to ensure that every node and relationship is accurately represented. Additionally, overcomplicating the logic for distance calculation is a common pitfall. Writing overly complex recursive or iterative solutions can lead to harder debugging and an increased likelihood of logical errors. Instead, sticking to simpler techniques like BFS for level order traversal or DFS with clear base cases will make your code easier to understand, debug, and validate. This problem uniquely combines binary tree traversal with graph traversal principles, which is a key pattern to recognize. Knowing when to switch from thinking of the structure as a tree to reasoning about it as a graph is crucial for solving the problem efficiently. A strong optimization strategy involves merging the process of finding the target node with the graph conversion step. This reduces the need for redundant traversals and improves overall efficiency. In interviews, it's also essential to communicate your handling of edge cases clearly. For example, explain how your solution behaves when k equals 0 or if the target node is missing from the tree. This demonstrates your ability to write robust and thoughtful code. Be ready for follow-up questions, such as finding nodes within a range of distances or limiting traversal to specific subtrees. Finally, exploring related problems like binary tree maximum path sum or diameter of binary tree can help you identify commonalities and sharpen your approach to similar challenges. There are several alternative approaches to solving this problem, each with its own trade-offs. One option is converting the tree into an undirected graph and then using BFS to find nodes at distance k. This approach simplifies bidirectional traversal but requires additional memory to store the graph representation. Another method involves using recursive DFS while keeping track of parent pointers. This eliminates the need for explicit graph conversion, but you must carefully manage visited nodes to avoid revisiting parts of the tree. A third approach is to use pure BFS directly on the tree. By treating parent nodes as additional neighbors during traversal, you can achieve the same result without converting the tree into a graph. However, this requires more intricate logic to manage parent-child relationships dynamically. Each approach has its pros and cons, so choose the one that best suits the problem constraints and your coding style. Great job! To summarize, we tackled LeetCode problem number 863 by converting the binary tree into a graph and using BFS to find nodes at distance k. Remember, this approach is efficient and widely applicable to many tree and graph problems. Thank you for watching, and I hope to see you in the next session. Keep learning and coding. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!